Hi everyone, my name is Justin Pertle and I'm an AWS Solutions Architect. And today I'm joined by our Q&A moderators Stefano Bugliani, Rahul Serene, Kyle Summers, and Chris Munns, who all of us specialize in some way in serverless computing and serverless technologies. And we'd like to share with you today best practices for securing your serverless application on AWS. But first, for those who may not be familiar with serverless, we'll cover a quick overview of serverless computing, including an overview of AWS Lambda, API Gateway, and Amazon Cognito, followed by best practices for how to secure your serverless microservices, then conclude by discussing auditing and logging as additional security measures. We will have time at the end for live Q&A, so please be submitting your questions throughout the session, and our moderators would be happy to help. For those that may not be familiar with serverless, serverless is a new computing paradigm, which means fundamentally that there are no servers to provision or manage. You simply write your code, and your code scales with its usage, where you pay for the invocations of your code and the time it runs, but you never pay for idle time, and availability and fault tolerance are built in, as you would expect from an AWS cloud service. To show you a little bit more about how this paradigm is growing and very real today, these are a sampling of some of our serverless customers who are using serverless technologies in production now, and the list is growing all the time as people find the benefits of this new paradigm shift. Today in particular, we'll focus on serverless microservices, which is a very common pattern and one that's important to really think carefully about security. So the best practices shared that relate to AWS Lambda and API Gateway can be applied to any of the other types of serverless applications, including data processing, stream processing, and others. So to start out, when you think of a microservice, whether you have a mobile application, a web application, or a third-party service that needs to integrate with your application, the first core thing that you need is a place to host your application code and to securely scale that code and that runtime to meet those needs. And in AWS, we have a service that does just that, which is called AWS Lambda. For those that are not familiar, Lambda is the ability to effectively run a function as a service and bring your own code. So today we support Node.js, Java, Python, and C#, including the ability to bring your own libraries from your own application runtime of choice. You have the ability to pick the scale of the function you would like to run, and you only pay for the compute time you use, metered in 100 millisecond increments. The important thing to know about Lambda is it will scale concurrently to your needs, but accordingly, it is stateless, so you do need to persist data separately in something such as DynamoDB, which is AWS's managed NoSQL database, S3, AWS's object store, or Elasticache, our in-memory caching solution. And Lambda effectively handles the rest and is a fully contained environment where you can have processes, threads, and run your code just like you normally would. So Lambda is there as our backbone of our microservice and our application and the foundation of our serverless technologies. But as we mentioned, we need a place to store our persistent state. So in a serverless microservice, we commonly pair Lambda with Amazon DynamoDB, our NoSQL store. And we won't cover much on Amazon DynamoDB today, simply because it doesn't relate as closely to the serverless security patterns we want to highlight. But know that there are other resources out there that we will share that you can leverage as well. And this is just one of the data stores that you can use with serverless technologies. So to highlight the final component that we'll touch on as part of our serverless microservice, we need a way to be able to route requests, to process the incoming traffic, and to compose a full RESTful API using our Lambda functions. And that service of choice is API Gateway from AWS. So we will cover these three as our showcase stack of a serverless microservice and dive in deeper. To talk to you a little bit about what API Gateway does for those that are new, API Gateway allows you to create a unified API front end to front multiple microservices or multiple Lambda functions as a unified resource and endpoint. You have DDoS protection and throttling built in, and you have a variety of mechanisms to authorize and authenticate your users to your backend requests. And then you have the ability to additionally throttle, meter, and monetize your API as well. So to dig under the covers a little bit, if you were to zoom in on API Gateway, this orange box represents the internals, where you can see API Gateway leverages CloudFront, our CDN and content delivery solution. And CloudFront enables additional DDoS protection for API Gateway, as well as having optional caching for your API responses, metering, logging, and monitoring via Cloudwatch, and most importantly, the ability to integrate with a variety of backend resources, ranging from Lambda functions as a direct component, or if you want to embrace a more server-oriented architecture, you can have API Gateway front EC2 instances or an Elastic Beanstalk environment. Or if you have components that are running even outside of AWS, API Gateway has the ability to front any publicly accessible endpoint. So now that we have our complete microservice and we have our functional, stack needed to be able to process requests, there's one thing that's missing, which is how do we know who you are, how to authenticate you. And so today in a modern application, identity tends to be one of the focal points of the key components to think about first in your application about how to manage your users, authenticate your users, know what they should be authorized to do. And for this, when you go to start this process, at first glance, it may seem that you can develop a homegrown auth infrastructure solution. But when you go down this path, you quickly realize that there are a lot of complexities, from being able to securely store passwords, to manage and scale a user directory that can scale to thousands, hundreds of thousands of users, to implementing multi-factor authentication, and even more commonly, identity federation, either with consumer identity providers or corporate identity providers, such as Active Directory or Shibboleth, for business to enterprise applications. So when you start to look at all of these different concerns, something that might seem simple at first quickly becomes more complex. And thankfully, we have a service in AWS called Amazon Cognito, which has two components that can solve these needs. The first component is something called Cognito Your User Pools, which allows you to easily and securely set up sign up and sign in functionality for your application as a cloud-managed identity provider. And additionally, we have Cognito Federated Identities, which allows you to federate identities from Facebook, Google, or any OpenID Connect or SAML provider of your choice to directly access AWS resources after federating and authenticating from those other providers. So to show a bit more, whether you are trying to use a social identity provider such as Facebook or Google, you want to have username and password login, or your own federated login with a SAML provider, all of those are possible with Cognito. And Cognito allows you to talk directly to AWS resources, to authorize access to your APIs and your API gateway resources seamlessly, or to connect even to third-party applications where you'd like to integrate Cognito as well. So now that we've talked about Cognito, you can see it as an additional and final component to complete our microservice, where you would first authenticate with Cognito and then be calling into our microservice. So now that we've covered the basics of a serverless microservice, let's dive deeper into the different components. For those that haven't used these services directly before, you may want to review this section a little bit later after using them firsthand, just because there is sometimes more to learn at first. So the first service to secure, as we mentioned, was AWS Lambda. And if you look at AWS Lambda, we have three different invocation and execution models that are present. We have a push model to respond in a request response manner from an API invocation. So when you use Lambda with API Gateway, this is the model that we're adhering to. And Lambda is directly responding back, and API Gateway fronts the response back to the customer. This is all synchronous. Additionally, we have a push model, which is asynchronous, which is when you have a trigger-based, event-driven architecture, where maybe you upload an image to S3, and then the image triggers the Lambda function to run to resize the image into a proper thumbnail. Or you put a message into SNS, and that triggers the Lambda function. These are also a push and trigger-based event, but the difference is they're done asynchronously. And the final execution model that we have available at AWS Lambda is a stream-based execution model. So with the ability for Lambda to read and consume a DynamoDB or Kinesis stream and consume the changes to those streams. When you look at those resources that are a push model, so things like triggering from S3 or tying to API gateway for synchronous calls through your serverless microservice. To secure this, we need something called a resource policy, which you set the resource policy on the Lambda function to grant the other service the permissions to invoke the function directly. And they also make it easy to set up cross-account permissions if needed. So to make that more clear, this is an example of an S3 bucket where I've put some images, and I want to effectively have a Lambda function generate my thumbnails. If you look, when you go into the Lambda console, you have the Triggers tab, and you can add one or more triggers here. And in my case, my generate thumbnail function, I've created a trigger where anytime I upload an object to this bucket, I will go ahead and trigger the function. Even though this UI is simple at the top, what it's doing dynamically as you add triggers is it's creating and modifying your function policy. So if I expand that, you can see that what this policy allows is my S3 bucket to actually fire the Lambda invoke function call, particularly from this particular bucket. So you can see the triggers dynamically create your resource policy and for you for the function. Additionally, we have lambdas that follow a pull model to read from a stream like Kinesis or DynamoDB streams. And for this, we have something called an IAM, which is Identity and Access Management in AWS, execution role. And an IAM role allows you to create one or more policies that are assigned to that role that is then assigned to Lambda that allow it to interact with other resources in AWS. So in this case, this is a different Lambda. Well, you can even see here, actually. So my generate thumbnail function needs the ability to actually write to a different S3 bucket, the ultimate thumbnail that I've generated from my Lambda function. So to allow Lambda to talk to an S3 bucket, I need an execution role. And if you see what I've circled here in red, this is my Lambda S3 execution role that has a policy that lets it talk to S3. Similarly, if you had a function that didn't have a trigger, but needed to read a stream on a scheduled basis, you would assign it an execution role that gave it the ability to read the DynamoDB stream or the Kinesis stream using simple IAM policies. Some other best practices related to Lambda security. In general, because you have these execution roles for Lambda, as a best practice, it's best for these to not be overly broad in their privileges, allowing malicious code to potentially interact with things that it shouldn't be able to, and to even have them as granular as one execution role per function. For me personally, if I say in our serverless microservice, if I have a /customers or /orders resource, I may have an execution role for my multiple Lambda functions that effectively do create, read, update, and delete orders that let me talk to my DynamoDB orders table. And so in that case, a few functions using the same role may be fine. But you don't want to have the entire API use the same role or an overly permissive role. Additionally, Lambda functions, like any other computing environment, also need and leverage secrets to interact with databases, connection strings, third-party APIs, and more. And for these secrets and configuration metadata, you're able to include them in environmental variables and then further encrypt them using KMS and Lambda's encryption helpers. And I'll show you how this looks in just a moment. We have yet another option for secrets management at scale called EC2 Systems Manager Parameter Store. Both of these are an option for how you can manage your secrets. To show you that firsthand, if I go back into my Lambda function and I go to my code tab, you can see at the bottom I have the ability to set environmental variables. So in this case, I'm setting up a DB password. My password is password, not a recommended password. And by default, if I just store any environmental variables, they are encrypted at rest, but anyone who could get in the console to look at the function could read them. And inside your computing environment, they will be exposed as plain text as an environmental variable. But we do, if you toggle this box, as I have, called Enable Encryption Helpers, you'll notice that we get these buttons to the side that allow you to click Encrypt and Code. And when I click Encrypt, what that does is it changes my password from plain text to a ciphertext blob that's now encoded and encrypted. And whenever I read that variable from my Lambda function, I get the encrypted blob instead. Now you might ask, well, how do I decrypt it in Lambda? And that's what the Code button does. So when I click Code, you can see some boilerplate code. This happens to be a Node.js function. So you can see this is Node.js here. But this code will go through and basically look and see if the secret has been decrypted previously. And if not, it will decrypt it when you first instantiate the Lambda container. And then that's only inside your runtime, only encrypted as needed on demand, and your secrets are much safer this way. And then you can use it as you would any other secret within your code. I mentioned there was another alternative, which is a service called EC2 Systems Manager, or AWS Systems Manager. And there is a component of that service called Parameter Store. And Parameter Store makes it easier not just for serverless applications, but for any application in AWS to securely store and manage secrets at scale and configuration values. So here, yet again, I'm taking my DB password, the same password as before, but I'm choosing to create this parameter as a secure string. And when I do that, I can pick my KMS key of choice. And also with Lambda encryption helpers, I'm also able to select the key. I was using my data lake key, which is my own managed key in both cases. And when I do this, and I choose the value, and I click Create Parameter, it immediately encrypts the parameter with KMS, so it's now ciphertext and not retrievable in plain text, unless I have the decrypt permissions to that particular managed key, and the permissions to also read this parameter. And if I do, I can call the decrypt operation to decrypt it. Now you might ask, when should I use this versus the Lambda encryption helpers? And the simple answer to that is, if it's a one-off secret where you maybe only need it in one function or something like that, then the encryption helpers work really well for that single Lambda function. But if it's something where you're going to be rotating a password on a regular basis, or you need to have that secret be exposed to many functions, then the EC2 parameter store is much easier because I can go in one place, only one time, to update my secret. And then all of my other application code at runtime will pick up that secret and be able to use it with the latest value of the rotated password. Some other best practices and things to think about with Lambda. Even though you're not managing servers in a serverless world with Lambda, you are managing code. And in today's modern applications, most of the times you're taking dependencies on third-party components. And so when you look here, those third-party packages and components, even though you don't author them, they can be subject to vulnerabilities. So as a best practice, I encourage you to think about how to continually scan for any vulnerabilities in your dependencies that you're using. This can be integrated as a step in a continuous integration and continuous delivery pipeline. And the vendors listed at the bottom left had solutions to help with these areas. Additionally, even though Lambda is code and it is fronted by API Gateway in our model of a serverless microservice, you still want to be thinking about input validation and sanitation, so you're not subject or at risk to something such as a SQL injection attack. And so all of those practices that you already know or have thought about are still things that you should be mindful of with serverless architectures. That was a look at Lambda. Now let's talk about API Gateway itself. So with API Gateway, The most important thing you want to be able to do is to authenticate users and then authorize them to properly access either all of the methods and operations in your API or a subset of those operations. And for doing authorization with API Gateway, we offer 3 different options for you. The first is something called User Pools Authorizers, which is meant for any user of Cognito user pools. Then we have Identity and Access Management, or IAM-based authorization, which is the same type of authorization AWS uses for all of its APIs. And the final type is called Custom Authorizers. Let's dive into each of the 3 more closely to provide an overview. First, we'll start with User Pools Authorizers. So as part of a user pool with Cognito, you take your application, you authenticate, which uses something called Secure Remote Password, which is the benefit of that is the password does not transmit in plain text over the wire, even under a TLS connection. Instead, a validator is sent to Cognito user pools. So this is a best practice. But however you're authenticating with user pools, once you've successfully authenticated, Cognito will return to you back a set of tokens for an authenticated and signed in user. And these include an identity token, an access token, and a refresh token. And if you haven't heard of these before, these are defined as part of the OpenID Connect specification. But the identity token, all 3, by the way, are signed from Cognito and can be verified with public key cryptography that they're valid from the valid user. But as a user, the identity token basically says, I'm Justin, this is my first name, this is my last name, it's my email, and any attribute of the user that the application is authorized to see is all encoded and signed in the identity token. So with a user pools authorizer, once you've signed in, the application is then able to submit a call to API Gateway and put in the identity token into the authorization header. And API Gateway then looks at the identity token and validates it using the signature to see if it's from the authorized user pool. And if it is, then it would go ahead and invoke the API call to AWS Lambda. And then Lambda would go ahead using its execution role we talked about earlier to access DynamoDB, assuming you were a valid user. Now, if you were not, you would have been returned a 400 error up front, potentially a 401 or something else from API Gateway. So that's a look at user pools authorizers. These are good in answering the question, is this a valid user, yes or no? But what user pool authorizers cannot do is tell you, is this user an admin user or a basic user? Or could this user access certain types of operations and not others, unless you've configured different operations with different authorizers? So user pool authorizers are very good for APIs where you have user pools and you just need to know if someone's a valid user. And then that brings us to the more flexible options that have more granularity, which include IAM-based authorization and custom authorizers. With IAM-based authorization, we have another component here, which is the other part of Cognito. And the way this works is you first authenticate with user pools, and you get back your tokens for a user. But at this point, you just have those tokens. The users don't have an effective role with AWS or a way to access AWS resources. And so what we can do there is we can take the identity token again and send it to Cognito Federated Identities to request AWS credentials. And after that's validated by Cognito, be returned temporary AWS credentials in the form of an IAM role that we've assumed. Now, for the sake of this drawing and this talk, I've included Cognito user pools at the top. But this flow would be the same if you were using a third-party identity provider or Facebook or Google or something else. You could have any of these flows start with an identity provider really of your choice, as long as it's OpenID Connect or SAML based, and then federate with Cognito Federated Identities to get your IAM role. But once you have your temporary AWS credentials, then you call API Gateway just as before, but you sign the request this time. So instead of just having a simple sort of token you're injecting, you actually sign each request uniquely based on what you're accessing, what you're trying to do, and the timestamp. An API gateway is able to look at the signature, determine what role it was signed from, check the policies on that role, and assuming you have access, then go ahead and invoke the Lambda function just as before, and the Lambda function could talk to DynamoDB. Now, in this particular situation, if you did not sign it properly or signed it from a role that did not have access, API Gateway would return, a 400 to you yet again. So for IAM-based authorization, a key thing to know is, the reason it's IAM-based is it's the same signing that AWS uses, and it uses IAM policies. So just to kind of show you a particular policy as an example, with API Gateway, we have an action in IAM called execute API invoke. And this is the key action used to allow or deny access to different resources and operations in your API. So in this particular case, I have an API with unique ID FF5 something. And what I'm doing here is I'm allowing, with a star at the end, invocation of all of my API methods, with the exception of the deny statement at the bottom, which is to do a post method on the /locations resource. And so effectively, I've given someone the ability to do everything except create a location, which is a post. So this is just a sample of IAM, but you can go very granular down to the method, the stage, and the resource to decide the authorization level that's appropriate for your users. And then the final type of authorization, which is the most flexible, is something called custom authorizers. And just like before, we would first go to our identity provider of choice, whether it's something you've developed or a third party. The key thing is that you need to be able to authenticate with that provider and get back some sort of bearer token that validates you as a user. And once you have that token, ideally a signed token or signed and encrypted token, you're then able to call API Gateway with the token in the authorization header or the header of your choice. And API Gateway will basically look to see if it's seen this token before and if it knows what the user can do. And if it doesn't have that token cached with a known policy, then it will go ahead and invoke a custom authorizer Lambda function, passing in the token in the event, and allowing the Lambda function to go out to the third-party identity provider to validate the user, to do any additional business logic around which groups or permissions the user should have, and dynamically build and return a well-formed IAM policy back to API Gateway. Once the policy is returned, we validate the IAM permissions in the policy against the policy, and assuming the user has permissions to access the method and resource of their choice that they are trying to invoke, we would then go ahead and invoke Lambda. Now, the nice thing with custom authorizers is the second time that we go to request and call this API as a user, our token that we used when we signed in would likely already be cached. And so the second time, there's no need for us to go to fire the Lambda function to go out to the third-party identity provider. We would instead just go direct to validate if we have access to that in our policy, which is cached, and if not, be denied, or if we do, go ahead and invoke the Lambda function. So custom authorizers are the most flexible, given you write all of the business logic in your Lambda function. Just to show you a little bit of sample code, at first glance, it may seem daunting to think, how would I write a Lambda function to create a well-formed IAM policy? But we have with AWS Lambda the concept of blueprints, which are boilerplate code and samples that you can customize and tweak. And this is a very basic sample built on the boilerplate for an authorizer in AWS Lambda. And you can see it's as simple as saying I want to allow a post on /locations, I want to allow a delete on /locations, and then I want to ultimately return the policy. And there's nothing else. And then of course deny statements also work. But I was able to get my first custom authorizer function working within 10 minutes time using the blueprint. So it really doesn't take as long or maybe as much effort as you might think at first glance. And then to recap, we have all three types of authorization available. But as a best practice, the one that I would encourage you to consider is the IAM-based authorization from AWS. The reason for this is IAM-based authorization signs each request uniquely based on the method you're calling, the resource you're accessing, and the time that you're making the action. Versus the other two, which send a token that is time limited, but generally good for 1 hour, to the API. So if somebody got your token and before it expired, they could access things in those APIs, on your behalf that you may not want to authorize. Whereas with IAM authorization, even if they intercepted the plain text of the request, the signature on that request was only good for one particular action at one particular moment, and there's not a security issue there. Additionally, to make this easier, because there is request signing involved with IAM-based authorization, API Gateway can generate SDKs in multiple languages that do IAM-based signing and SIG-v4 signing out of the box. SIG-v4, by the way, is the same thing as IAM signing. It stands for Signature v4, and it's the method AWS signs requests. And then the only other type of authorizer that is also potentially a good option if IAM authorization isn't available for you, but you still need to have more than yes/no authorization for your users. You need to differentiate admins or standard users or something else, is custom authorizers, where you can write your own business logic of choice to go through and do the right decision making. So that's a look at authorization. Additionally, API Gateway provides many other security benefits as well. So I mentioned DDoS protection, which is provided out of the box via integration with CloudFront and a lot of hardening in our AWS services. We further offer the ability to do throttling for your end users. So not just throttling if you're using AWS, but throttling in the sense if you want to ensure that your backend resources are not overly leveraged or exhausted by one particular consumer. And so the way this works is you have the ability to create something called usage plans. So one particular consumer, can be a professional plan member. Another consumer can subscribe to the premium plan, or another in the enterprise plan. And these plans can be defined both in terms of transactions per second allowed and the maximum amount of calls allowed per day. And so just as an example, in this case, a professional plan might be 10 transactions per second with up to 100 calls per day, but an enterprise plan user might have 500 transactions per second, but no limit on the total calls possible. The way these work is they work via API keys. So you create one or more usage plans if you're looking for this kind of feature. You set the quota on the plan, and then you generate API keys that are subscribers to those plans. And then when the user calls API Gateway, they pass in their API key, which associates them with the plan, and we keep track of the metering per key for you. And then if say you want to monetize your API to charge people maybe based on just what they use at the end of the month, you can also generate reports to show what the usage was per API key. Now, one note on API keys. You can configure API Gateway to require API keys for a given resource, and some may think of that as a method of authentication. But as a best practice, we would encourage you to not think of that as an authentication mechanism, but rather a mechanism just to control quota and usage. And instead, make sure you're sending an authorization header using one of the authorizer choices we mentioned before. The reason for this is an API key is a static key that doesn't change for a consumer over time. And so if someone were to intercept a request and be able to read or leak to your API key, then that would be all they would need if you didn't enforce other authorization types to be able to access the API. All of the three types we mentioned before of authorization present are all time limited in nature. They all rely on tokens in some way, and those tokens are generally only good for 1 hour. So they're much more secure than an API key for authentication. So to show you an example serverless architecture, Here is an example of a static website with a serverless backend. And just to show you, I know we haven't spoken much about CloudFront and S3, but CloudFront provides the ability to do DDoS protection. It provides the ability to do private content. So if you have certain pages of your site that shouldn't be exposed or others, and then S3 behind it with different bucket policies and ACLs. This can host a fully serverless static website, which can then integrate, as a single page app with your serverless microservice. So to overlay all the different techniques on one slide and one view for you, with API Gateway, we've had throttling, caching, usage plans. With Lambda, we've had invocation policies and execution roles. We've talked about secret storage. And even though we haven't covered DynamoDB as much, IAM plays a part with DynamoDB as well and provides a lot of granularity with fine-grained access control. So this is a complete picture of a serverless microservice and a serverless web app to go with it. Now, to cover a bit more, another concern with any kind of security is, of course, auditing and logging. And so when it comes to auditing and logging, Cloudwatch is our de facto monitoring metrics-oriented service and the service for log streaming in AWS. So for API Gateway, for Lambda, for all of the services you just saw, they all integrate with Cloudwatch to provide built-in metrics and alarms. And you have the ability, if you're submitting your own custom logs, to create custom metrics with a metrics filter of your choice. So this will stream, for instance, for Lambda functions, all console statements or logging outputs get streamed into Cloudwatch logs. Or other things, if you want to turn on logging with API Gateway, you can log all requests and all responses, even optionally including the payload if desired. Cloudwatch can handle all of that. And then some customers, particularly if they have multiple accounts, like to leverage Cloudwatch logs in conjunction with Amazon Elasticsearch service for near real-time streaming, which can be set up with just a few clicks. So that's how you can aggregate all of your logs. To show you just a glance all the different logs available, you can see all these different services. And then when you think about security, pretty much every log related to any of these serverless services is in scope for security-related events and something you would want to be actively monitoring over time, whether it's API Gateway, Lambda, or more. Additionally, there's another type of logging that's very important from a security perspective in AWS, which is AWS CloudTrail. And what this does is this records AWS API calls for your account. So who made a particular call, what call did they make, when was it made? All of these types of details are found in a CloudTrail event. And CloudTrail is able to aggregate them into an S3 bucket and to a Cloudwatch logging orientation where you can basically retroactively analyze these logs over time. There's a companion service that goes with CloudTrail that I consider better together called AWS Config, which I encourage you to turn on if you haven't seen it before. And the way this works is it goes and it inventories all of your AWS resources. So in the screenshot here, you can see an inventoried IAM policy, and it keeps track of the relationship of that resource over time and the changes to it over time. So in this case, you can see in August 14th, I had been messing with my IAM policy, and on August 12th, I had changed something. And AWS Config allowed me to go back retroactively and figure out I was actually the one at fault when I broke a live streaming deployment that I had changed an IAM policy. But I knew I made the change, and I could see the before and after text of the policy by using AWS Config. Additionally, Config offers something called config rules, which allow you to enforce key behaviors and best practices on your AWS environment all up. So anything from requiring EBS encryption to other types of policies you may want to enforce. And in summary, we've covered an overview of serverless applications, including our serverless microservice pattern of AWS Lambda, API Gateway, and Amazon Cognito. And we've dove deeper by looking at how do we secure each of those components and leverage them together, along with auditing and logging as a companion to meet our security needs. So I would like to go ahead at this time and thank you all for joining today. and also mention a few additional resources that are available on AWS. First and foremost is our Serverless on AWS computing site, which I encourage you to check out if you haven't seen it, as well as several reInvent talks and webinars that talk through many of these concepts even more in depth in today's session. And most importantly, I think in many cases, is to see the code in real life action. And we have several projects on GitHub that I'd recommend you check out, particularly showcasing Cognito or all of the API Gateway Authorizer options that are available for your reference, most of which can be stood up in just a matter of minutes. So all of these are available for you now, and I'd like to thank you again for your attendance today.